right, so there is a theorem, theorem 915. Sorry, I'm getting my tablet turned the right way. There we go. 915 in your book about remainders, which helps us figure out, like, if we wanted to add up the first 400 terms of the series and I want to know how close I am to actually getting to what the actual sum is, there is a theorem here to help us find that remainder and let us know how close we are, kind of our error, if you will. Okay, I'm going to let you read this on your own. There's one homework assignment or one homework exercise that refers to it, and normally I leave it out and just tell students I need you to read that. If you have questions interpreting it or using it in the homework exercise, please come see me. But also example 4 below it gives you an example of how the remainder theorem works. Same thing for finding the number of terms. There's one exercise that says how many terms do I have to add up if I want to be within 1/10,000th or 100,000th of what the actual sum. So finding how many terms. Okay, that would be reading example 5. They give you an example of how to do that there. And again, those are things that I typically send the students to the book for. And if you have trouble, of course, please come see me. I will help you with it, but I'm not going to lecture on it, nor would I have if we'd have met face to face. The remaining topic for this section is we're going to talk about absolute versus conditional convergence. Okay, me being lazy and abbreviating. Absolute convergence versus conditional convergence. Okay, one thing that's nice to keep in mind is if I am wanting to add up a series, if I take the absolute value of all the terms, and when I take the absolute value of that, if that new series converges, then that means a sub n without the absolute value will also converge. Okay. We call this absolute convergence. If my sequence instead in absolute value, if it diverges, but the sequence itself converges, okay, we say that a sub n converges conditionally. We call that conditional convergence. Okay, so an example of this is if I'm looking at the sequence -1 to the n over n squared. Okay. If I want to take the absolute value of those terms of this alternating series, then I'm looking at the series 1 over n squared. I know that 1 over n squared converges because it's a p series. Anytime the p is bigger than 1, that series is going to converge. Okay. So since the absolute value of those terms, I'm too lazy to rewrite the whole thing. Since that converges, then by default, okay, from our theorem up here, it's theorem number something, 916 in your book. And that means a sub n converges. Okay, that means this series is going to converge. It's going to converge what we call absolutely. Okay. The absolute value of all the terms, that series converged, which means the series without the absolute values will also converge. So we say that that's converging absolutely. I'm going to go down and up and down and up. If I want to look at the series -1 to the n power over n plus 3, if we take the absolute value of those terms, then that's our harmonic series 1 over n plus 3. Okay. This is a series we've worked with. If we didn't have the +3, we had a -3, but all of them, and I haven't said the word harmonic out loud, but your author has very much said it and used it through 9.3 and 9.4. Okay, when we have a series 1 over n+3, this one diverges. Okay, we had a lot of tests. We could use the integral test for this. We could use a comparison test. I would say the limit comparison test, because the inequality wouldn't go in the right direction for the direct comparison test. Um, but this series, hopefully we're very comfortable looking at it and saying, I know that series diverges at this point. Okay, but if we look at this series without the absolute values, alternating series test, 1 over n+3 does go to 0. That says equals 0. And it was supposed to say equals 0. Also, if I look at the n plus first term and compare it to the nth term, this is one that I don't have to have any kind of in-depth proof. I can say this because the denominator is bigger, so the fraction is smaller. Okay. The series converges by the alternating series test. Okay. The absolute value, if I made all the terms positive and I look at that series diverges, but the alternating version of that series converges. We say that this converges conditionally. On your homework exercises, there is a batch. There's going to be 2 parts of this homework assignment. I'm going to leave them separate in the computer, I think. Maybe not when I go to put them in. But there is a batch that says determine whether the series converges conditionally or absolutely, or whether it diverges. Okay, a good path to take, instead of starting with the series that you're given, okay, you can do that. But then if you decide that this one converges, of course, if it diverges, you're done. But if it converges, then you've still got to do this one. Okay. If you start with taking the absolute value of all the terms, looking at that series, okay, if you find out it converges, then you're done. You don't have to do another test on anything else, because we have the theorem 916 that says, well, that means the alternating series converges as well. Okay. But if the absolute value of the terms, like the one we just can still see up here, if that diverges, then you've got to still do a test. I think all of them in this section will be an alternating series. Okay, so we do the alternating series test to see what happens to A sub n. So when we're testing for conditional or absolute convergence, again, it will set you up for the shortest path if you start with the absolute value. Because if it converges, then you're done. You don't have to check the other one. If it diverges, then you do have to check the other one. But it can save you some time if you go in that order. Okay. I will be available. I'll be in and out of my email over the weekend if you need to get a hold of me and ask questions about this. I will try to get these uploaded to YouTube and then into Canvas soon, and hopefully by the end of the day today, which is Thursday, you'll have access to them. So thank you much.